All right, that's noon, so we might as well get started. Welcome back, everyone. Today, as I said a moment ago, my plan is to finish up on Chapter 7, and there's essentially 3 topics I'd like to cover. The first of which is Markovnikov's rule, and my emphasis there, I almost don't even really care if you know that it's called Markovnikov's rule or can spell it in particular. Mr. Markovnikov might care. I don't really care. My main hope is that everyone will know what it says and be able to apply it, even in the situation of a structure that you've never seen before, which perhaps you've noticed by now, OWL is pretty good at coming up with structures you've never seen before. And not to brag or anything, but I think I'm no slouch in that department either. So that's basically the idea, is learning how to apply it, what it means for us, and then how to apply it. I also want to spend a little bit of time talking about the structure of carbocations. What do they actually look like? Since we've largely covered carbocation stability, that came up in an OWL question a couple chapters ago. And by the way, that will happen sometimes, that you will need something in an OWL question that we haven't talked about in class, might even be in a future chapter. I did double check in that case, and indeed, OWL did tell you everything you needed to know in order to be able to solve the question, but I had no problem going over that in class, a week or two early, and so I won't go as in depth into that this time, but that's going to happen sometimes. And then they did actually give you enough information. So since we've already talked about carbocation stability, what we're basically going to learn about in Markovnikov's rule is why it matters, why we should care how stable this or that carbocation is. That's basically going to be the application here. And then I do have a reef session for you guys with actual polling questions this time. We'll go over that. And then what I would like to end with is carbocation rearrangements. And you guys need to stay on me because I need to be sure to get that last example correct, because I kind of screwed it up in the previous class. So probably we'll get to see YouTube. Hi, YouTube. And I need to be absolutely certain that I don't screw that up. So I'll be very careful. And it's hard because it's the last thing I'm saying and my attention's wavering, your attention's wavering, but I got to keep it up till the end. So, and that's basically it. Since we've already covered the Hammond postulate, that will basically then be it for chapter 7 and the exam material. My plan then is on Friday to start chapter 8. That material will not be on exam number 2. That'll be in exam number 3. And then that actually brings up another thing. I'm fairly confident that you're going to wind up having a bye week on OWL. I don't think it's this week, but next week, because we won't have finished chapter 8 by Friday. We're finishing it the following Monday. So I'm not going to make the OWL assignment due that Friday if we haven't finished the chapter in class yet. So that will happen sometimes, that you'll get a bye week. Usually happens about twice in the semester. So that doesn't come as a surprise to me. That's another thing that you will always be able to trust. If there's nothing due on Friday, then there's nothing due on Friday. Just be sure you're always looking at view all assignments, because sometimes that messes things up for reasons I don't entirely understand. But that will sometimes happen. I would certainly never do something to you guys like putting up an assignment on a Thursday that's due the next day. I would never do that to you guys. So you can always trust that. If you see on a given Friday that nothing's due, nothing's due. You don't need to worry about it. Good. So what then is Markovnikov's rule and why should we care about it? Well, I have a bit of a confession to make, which is that the examples we've been looking at so far of addition of hydrohalic acids to alkenes or hydrohalogenation of alkenes, all the examples I've given so far, you could say I've carefully picked the alkene starting material to be symmetrical, like in our reef session the last time. I feel like this thing's awfully loud. I don't know if I have a way of turning it down, but be that as it may, I guess I'll just have to turn myself down. Anyway, So I've carefully chosen the alkene starting materials to be symmetrical so that it wouldn't matter which way the hydrohalic acid added. You'd get the same thing. We had an example like that in our reef question last time. But what if the alkene starting material is not symmetrical? Like, say, this guy. We can call that what? How about 2-methylpropene? That works for me. Of course, there is no E or Z or cis or trans, because this carbon is 2 methyls, that carbon is 2 hydrogens, game over. There's no stereochemistry. But you'll immediately see that now there's 2 possibilities for the product. And which one are we going to get? Well, again, I'm cheating. That's actually a trick question. Which one will we get? We will actually get both, but thanks to Markovnikov's rule, we're able to predict with some confidence which of them is going to be the major product. And that's going to turn out to be this one. That's going to be the major product. We're going to get more of that. We probably will get a little bit of this too, but that will be the minor product. And I don't know exact percentages. I would never ask you to speculate in such a thing either. But if you forced me to guess, I would guess that this minor product you'd get at most 2 or 3% of. Very little. I think the vast majority of the product will be that chloride as opposed to the other one. And that's what Markovnikov's rule does. It allows us to predict in cases where there's in principle more than one possible addition product, which is going to be the major product. Oh my, what's all this then? Good, okay. So that's what Markovnikov's rule is for. Now, let me take a break from the whiteboard just to point out that everything I'm about to say, I've written it all down for you in the class notes. So here I'm looking at the chapter 7 class notes. It's all there. So you don't need to worry about getting every single possible golden word that comes out of my mouth. And what we find is, now everyone just stop listening. Didn't mean that. But be that as it may, one word that I wanted to be sure we defined, and I also defined that in the class notes, it's all here. You might have heard me using these terms more substituted and less substituted. You can talk about a more or less substituted alkene, or a more or less substituted carbocation, or really a more or less substituted anything. And basically, the definition of more substituted in that context, and I wrote that down on the whiteboard here too, that definition is more non-hydrogens directly attached. So usually more alkyl groups, but certainly more non-hydrogens directly attached, fewer hydrogens directly attached. And if another alkene or carbocation or what have you, you can use it in any similar context, is less substituted than the other, then that means that there's more hydrogens directly attached, fewer non-hydrogens directly attached. So, and again, that definition is in the class notes. So with that being said, there's 2 ways to state Markovnikov's rule. There's kind of the older classical statement, which I'll start with, even though I'm not a big fan of it. And then there's the more modern way of stating Markovnikov's rule, which has much more explanatory power. And while I'm certainly not going to tell you that you cannot memorize the classical statement of Markovnikov's rule, you know how I am on that matter. You've heard me say this before. This is America. You can memorize whatever you want. But I think you'll find that the more modern statement is much more helpful. They're both still true, and they really are both saying the same thing. It's just that the more modern statement has more explanatory power. Both of those versions of the statement are for the same thing. They help us to predict what the major product is going to be. In cases like this, where you're adding an unsymmetrical reagent to an unsymmetrical alkene. And HCl, HBr, HI, this is just one example of such a class of reagents. We'll get a bunch more like that in chapter 8. We'll also discover that some reagents that can add across an alkene are symmetrical, like H2. You can probably already guess what'll happen if you treat an alkene with H2. Well, you turn the double bond into a single bond and you put an H on both of them, And so now it doesn't matter that the alkene is unsymmetrical. But Markovnikov's rule is for figuring out what's going to be the major product in cases where both the reagent and the alkene are unsymmetrical. Up till now, I'd been carefully handpicking alkenes that were symmetrical, so there was no issue. But now we need to dive into this issue. So one way of stating Markovnikov's rule, again, the older way, is that if you treat an unsymmetrical alkene with an unsymmetrical reagent, the major product will be the one that you get from the hydrogen of that reagent going to the carbon with more hydrogens directly attached, or the less substituted carbon, if you will. And the other piece, whatever that might be, for us so far, that's going to be chlorine, bromine, or iodine, right? Since it's HCl, HBr, or HI. And that piece is going to go onto the more substituted carbon, the one with fewer H's directly attached, more non-hydrogens directly attached. And again, this is perfectly true. It's not wrong. There's nothing wrong with that statement, except it doesn't really help you understand what's going on. And it doesn't fit in with our mechanistic understanding of the addition of HCl, HBr, or HI to an alkene, since we know the mechanism. That's why I'm saying this is the older form, the classical form of the statement, that was made really before we had today's understanding of the mechanism of the reaction. This would be if, this would be the way your grandparents learned Markovnikov's rule, if any of them took organic chemistry, or my parents. Actually, my mother was a chemistry major, which is probably part of the reason I am the way I am. But that would be the way she learned it when she went to college in the mid to late 1950s. So another way, and I think a much better way of stating Markovnikov's rule, and again, this is all in the class notes. I've given it to you straight out. And that says the following, that when you react an unsymmetrical alkene with an unsymmetrical reagent like HCl, HBr, or HI, the major product is going to be the one that comes from the most stable possible carbocation that you can get. So, and that's something that we understand about, because we've gone over carbocation stability. We understand that other things being equal, more substituted carbocations are more stable than less substituted carbocations, for example. And that is a much more helpful way to learn Markovnikov's rule. That's going to actually help you to predict what's going to happen, even in cases where the starting material is an alkene that you've never seen before. And this also ties it in with the mechanism. It makes it almost part of knowing the mechanism. And I should say, Markovnikov's rule is going to come up repeatedly, both the rest of this term and next term. It's going to apply in cases where we have a carbocation intermediate, and it's going to help us to predict what the major product of a reaction is. Now, certainly not every reaction is going to, there's the statement of, oh, wait a minute, hold on. So there on your screen now, if I can fit it, you can now see both statements of Markovnikov's rule. It's in the class notes, so you don't need to worry about that. I've already given you both forms of the statement. So, but that's, I realized I wasn't sharing that screen. So, where was I? Back to the whiteboard, I think I had something there. Good. So that's where Markovnikov's rule is going to come into play when we've got a carbocation intermediate. Now, not all reactions have a carbocation intermediate. Some do, some don't. But where there is a carbocation intermediate, we're going to find that we've got a chance at applying Markovnikov's rule. And that's especially in these addition reactions of electrophiles to alkenes. That's where Markovnikov's rule is especially applicable. Good. So now you can see how Markovnikov's rule works out here. Here we've got an unsymmetrical alkene. And yeah, the older form works. The H is going to go for the major product to the carbon with more H's on it, and the chlorine is going to go to the carbon with fewer H's directly attached. And so this compound's going to be favored over this one. But Markovnikov's rule also says that you can predict the product based on the stability of the intermediate carbocation. And that's not something you've memorized beforehand. That's something you figure out based on what you're given. Here we're given, whoops, that alkene. And so let's work out the mechanisms and see if it's true. See if we can tell which of the two possibilities gives us a more stable carbocation than the other. So we'll start here. One way that this can react is for this bond to swing out this way. So it's going to remain attached to this carbon, and it's going to swing away from the other carbon and leave a plus charge there. The electrons in this bond will form a new bond between this carbon and that hydrogen. And then, of course, we lose our halide ion. And as we follow that along, I think you'll agree that we're going to get this carbocation. And the H's are understood. You can write them in. If it's better for your learning style to write everything out explicitly like that, you can. It's not wrong. It's just that if you use line angle drawings, then the H's are understood. So this carbon now is a methyl group. And of those three H's, two of them were there to begin with. One of them we just added from the HCl. And we leave behind this carbocation. Again, the way we know that is because we swung the bond away from this carbon. And so that carbon is going to be now electron poor. And so it will have a plus charge. Naturally, the next step of the reaction involves the chloride attacking that carbocation. We'll use whatever halide we're given. That's how we know what to put there. And that will then lead to that major product. Meanwhile, there's another way that this can react. The bond can swing out this way. And you'll notice that I'm comfortable with putting the HCl on either side. You don't memorize that the HCl goes on the right. That's not how to learn this type of reaction. You need to be equally comfortable drawing it in the other direction. That should be the same thing for you. Shouldn't be any harder or trickier. When we do that, the electrons in the pi bond are going to remain attached this time to this carbon. And you're going to form a bond between that carbon and hydrogen, and then leave behind a plus charge on this carbon. Wait a minute. For the first reaction, is the arrow coming from the bottom double bond? It doesn't matter. If you had drawn it like this, I would not even notice. So what that means is you need to practice until you see that those are the same thing. So that doesn't trip you guys up. But I see those as the same thing. Good. This, though, is very different, right? Because now the bond is remaining attached over here, and we're taking electrons away from that carbon. That means that now our plus charge is going to be on this carbon. And again, if you want to draw in that other hydrogen, if that's better for your learning style, you can. It's not wrong. But if you use line angle drawings, then the hydrogens are understood. So now we get this carbocation. And again, in the second step, and always remember it's two separate steps in this reaction, that chloride ion is going to attack over here, and that will lead to the other product, the minor product. And now you can see, if you compare these two carbocations, this one is tertiary, and this one is only primary, because that carbocation is two H's directly attached, along with the alkyl group. This carbocation only has three alkyl groups. In this case, they're all three methyl groups directly attached. I didn't know that beforehand. That wasn't something that I had memorized previously and regurgitated. That was something I figured out based on what I was given. And that's what I would expect all of you guys to be able to do. Yes?
So when you're drawing the major product, where the bond is swinging this way, right?
Right, but if you're asking in the major product, is the bond always swinging this way?
Oh yeah. So when the major product, the bond is swinging this way, when you draw it, does it matter which way the arrows go?
It does matter, unless you're talking about like up versus down. That doesn't matter. Right versus left matters. And the way I have it here is the way you need to do it to get credit. And I think the way that you know what it means, I think you can see that if the arrow is going this way, it's like it's swinging away and leaving this carbon here without a bond. Likewise, going this way. Now, I mean, you could just as easily, I suppose, have turned the molecule around. I don't want that to be a big deal to you guys. Like it's extra effort to pick which way to do it, but this would be equivalent. So I don't want you to memorize that one goes to the left and one goes to the right. Trust me, you're only going to make it harder for yourself. You decide what you're going to put down based on what you're given at the time. That's the best way to go about it. Good. How is this carbon primary? Because there's only one alkyl group attached. We defined a primary carbocation as having one alkyl group and two H's directly attached. So, and again, that wasn't all that recently. It was actually, it was probably close to 2 weeks ago. But if you go back and review the definitions of carbocation substitution, you'll find this one's primary, that one's tertiary. So, no wonder that this is the major product. It comes from a tertiary carbocation, which is significantly more stable than the primary carbocation. And again, I didn't have that memorized beforehand. I didn't just know that this was primary and this was tertiary, and so therefore obviously that. But I was able to figure that out on the spot. And that's what I'm going to expect you guys to be able to do. You should work on this until, if you're given an alkene you've never seen before, you can work out any and all possible mechanisms, figure out by looking at what you have there, which is the most stable possible carbocation, and therefore that intermediate will then lead to the more stable product. And if you then know that that's called Markovnikov's rule, that's great. But if my choice is between you knowing it's called Markovnikov's rule and knowing what the rule says and actually being able to apply it to a molecule, even one that you've never seen before, I'll take the second thing. That's more important. Good, so that's one example of Markovnikov's rule. How are we doing in time? 12:30. Okay. I mean, I wish I had time to do other examples, but time is limited here. Yes? You can if you like. That's covered in the handout in chapter 6, the addendum. That talks about drawing dotted lines if you want to, and it shows you how to do it correctly. So that's in there for you. Good, other questions? Would tertiary lead to a major product and primary lead to a minor? Yes, that will always be the case, but I didn't necessarily know that I was going to have a tertiary and a primary. If one of them turned out to be tertiary and one secondary, the tertiary would win. If one were secondary and one were primary, the secondary carbocation would win. So again, I don't want you guys memorizing rules. I want you applying knowledge. That's the way to succeed in this class. And I said some of this to the previous class too. Please do not refuse to learn to master material and insist only on memorizing rules. Please. In my 22 years of teaching, which doesn't, God knows that doesn't mean I know everything. I've just kind of seen a lot, you know. That is the biggest obstacle to students doing well in organic chemistry, is they just refuse to learn to apply material. Please don't do that. That's going to be the biggest possible obstacle, I think. Good. Well, let me just go over one other thing. Let's very briefly talk about carbocation structure, since we haven't really gone over that yet. Oh, sorry, question. From the way I knew this was primary and that was tertiary was from the definitions I gave a few weeks ago. We defined what a primary carbocation is, what a secondary carbocation is, and what a tertiary was. And the definition of a primary carbocation is one that has two H's directly attached and one alkyl group. And tertiary is defined as 3 alkyl groups directly attached to the carbocation carbon. So if you go back, I mean just you, I'd say this to anyone, but if you go back and review the definitions we gave, I think you'll see that falls under the definitions. In this case, the alkyl groups are CH3s, but it would still hold if they were not CH3s, but other alkyl groups. Good. I can't see a thing. Other questions then? All right. We've already discussed that carbocations are planar triangular species. So you need to know that carbocation carbons are sp2 hybridized, and that's normally how we will draw them. You'll notice I've given my best good faith effort at showing 120-degree bond angles. We have this agreement, you and I won't get out a protractor on you if you don't get out a protractor on me. But if we were to turn that on its side, which normally we wouldn't bother to do this, but doing so helps us to see a little better what's going on. And again, I'm implying that anything can be attached to these bonds, can be H's, can be alkyls, anything. But when we turn it on its side like this, what we see is that on that carbocation carbon, we have an unhybridized p orbital. And that's the source of the plus charge, really, because that unhybridized p orbital is also empty. It's missing an electron pair. So that's how you know that the carbocation is a plus charge. Another way you can know that is because the carbon has 3 bonds and no lone pairs. And if you go back to how we determine formal charges, you'll see that in that case, the carbon comes out with a formal charge of +1. So this really is the nature of the reactivity and the structure of carbocations. They are planar species with the carbon atom being sp2 hybridized, no exceptions. They're always sp2 hybridized. By the way, we've also talked a fair bit about radicals. Radicals are actually really similar to carbocations. The only difference is in a carbocation, this p orbital, this unhybridized p orbital is empty. It has no electrons in it. For a radical, there is 1 electron in it, 1 unpaired electron. And so they're pretty similar species. Both are going to be sp2 hybridized with no exceptions. And they're actually both also electron deficient, aren't they? A carbocation is missing an entire pair of electrons, whereas a radical is missing just 1 electron. So I'm almost beginning to think I just can't wear my glasses. Another thing will probably keep falling down. I don't know. We'll see. We'll try it. Good. So, my point here is you need to know what the structure of carbocations is, that they're planar, the carbon is sp2 hybridized, and there's an empty p orbital. Yes? Well, is the carbon missing 1 electron or 2 electrons? It depends if you're talking about the electrons in the free atom or the electrons once we consider bonds in the octet rule. Normally, we're considering bonds in the octet rule, and in that sense, it's missing 2 electrons. Good, yes. I'm sorry? The reason that there are wedge bonds and dot bonds here, and the way that you know to do that is because I've turned it on its side, like this, and we're looking at it edge on. So this bond, if you turn this on its side, I'm basically rotating it around this way. And you'll see that if you do that, there's going to be 1 bond coming out at us and 1 bond going away. When we draw the carbocation in the plane, which is what we will normally do, then they'll all 3 bonds be in the plane. And in this case, that unhybridized p orbital would be perpendicular to the screen. So I just drew it this way just so that now the unhybridized p orbital would be in the plane of the screen. Neither of those is more correct than either of the other, but I would expect you guys to be able to do this and to understand what's going on when you see drawings like that. Good. Other questions then? As always, you guys ask so many good questions. So I think that's all I really need to say about that. That should be good for us to get into our reef session. So let me be sure that I select that. PowerPoint. Good. So, and as always, 8 of the 10 points are just going to be based on attendance. Good. So my first question, I'll start it in just a moment. A certain reaction is endergonic and has one step. According to the Hammond postulate, what does the transition state most resemble? And there is enough information here to figure this out. If I were you, I'd start by sketching a simple, I would start with just sketching a quick reaction energy diagram and then applying what we said a couple classes ago about the Hammond postulate. Well, endergonic doesn't exactly mean endothermic. And again, I can't really give individual help. I'll just say there's enough information there to figure it out based on what we said. But they are subtly different things. Let's go out to 2 minutes on this. All right, 30 more seconds, please. May we work together? Yes, you can work together. However, I don't think you're going to be able to look up the answer. You're going to have to figure it out. But there is enough information. Okay, another 10 more seconds or so. Anyone else? Last call for answers. Looks like that's everyone. Okay, well, let me give you a hint as to how to approach this. I will let you know, even though I just did this in my previous class, I don't know what the answer is. You need to figure it out. It's not a memorized rule that you apply. You just figure it out. So let's draw a simple energy diagram. You can put E or delta G or something like that over here. Here's our reaction coordinate. And so if the reaction is endergonic, that tells me that the starting material is lower in energy than the product, or the product's higher in energy than the starting material. Product's less stable. And if there's just one step, that tells me that we just go up through a transition state, through a local maximum, and there's no intermediates. It just falls down from that transition state to the product. So here's my starting material, here's my product, and here's my one and only transition state. There's enough information in the question to figure all that out. You don't even need to know what the reaction is. And I didn't even specify. This would be true regardless of what the reaction is, as long as it fulfills that description. So Hammond's postulate says that if we want to know what the transition state looks like, then we look at the two immediately surrounding real species, which there will always, without exception, be for every transition state. There's going to be two real species, one on either side. And the Hammond postulate just says the transition state looks more like the real species to which it's closer in energy than like the real species to which from which it's further away in energy. That means it looks much more like the product than like the starting material. And again, I didn't memorize that beforehand. I figured it out on the spot. And that's what I'm expecting you guys to aim for. So so what does that mean? We said it was the product that it more resembled. That means, to me, the best answer is B. Let's see what you guys said. Yep, that was the majority opinion. Excellent. Next, that was fairly challenging. Next one I think is a little bit less challenging. It's what we just talked about. What is the major product of the following reaction? We're reacting this with HCl. I think one of those is going to be the major product. So again, this is really what we just talked about. And it's a reaction we're by now familiar with. So we'll say another 40 seconds or so. We'll go out to 2 minutes again. All right, another 15 seconds or so, please. All right, last chance for answers, please. Looks like that's about it. Good, well, I'm going to approach this the same way. I don't know what the answer is. I'm going to figure it out. But if you're thinking that you should have the answer memorized and just be able to give it, that's not right. At least I wouldn't expect you to have it memorized. As I recall, our starting material looked like this, and we were adding HCl. Well, we're familiar with that mechanism. This double bond is going to swing out this way, pick up H plus from HCl, and kick out the chloride anion. So this arrow here means that we're, whoa, I screwed that up. Hold on. Once more with feeling. No, that was right. What am I talking about? It's going to swing away from this carbon and remain attached over here. Yeah, there we go. And so we're taking electrons away from this carbon. And the reason I know that is that carbon's more substituted than that one. That's going to give me the most stable possible carbocation that I can get. And so that's going to leave the plus charge over here. Again, the way I know that is because of how I'm drawing this arrow. I'm trying to show that it's swinging away from it's swinging away from this carbon and taking electron density away from that one and remaining attached to this carbon. That carbon's going to get the H attached. This carbon's now a CH2. There was one hydrogen attached there already. The other one we just got from HCl. And we'll leave a plus charge on the tertiary carbon, which is much better than putting it on the secondary carbon. Then our chloride ion attacks. Sorry, there's still that plus charge there, of course. And I would expect that we would get this compound as the major product. So the tertiary halide. So again, I didn't know beforehand. I mean, except I should have because I just did it in my other class. But you get my point. It's not something I've memorized ahead of time. So let's go find that product. That looks to me like C. So I think C is the best answer. And what do you guys think? Also C. Good job. Okay, so the remaining 8 points again are just going to come from attendance, which, by the way, I think I have the Reef gradebook, whether on the Reef website or on their app. I think I have that looking a little bit better. It's still not everything I would like it to be, but I think it should now be giving you 1 point per question plus 8 for participating, or else on days we don't poll, it'll just be 10 points for attendance. Good. So that's an example of applying Markovnikov's rule also. As long as the chlorine is attached to that carbon specifically, first of all, this does not have to be a chlorine, right? It could be HCl or HBr or HI. Does the location of the bond not matter unless told to indicate stereochemistry? I think the answer to your question is yes. I see this as the same as what we had on the other page, on the PowerPoint presentation. So that means that you guys need to practice until you see them as being the same, and that doesn't trip you up. And you know, you're not born knowing that, of course not. I would never expect you to be. That takes practice. Good. Any other questions on that Reef session? Good. Well, there's just one other topic that I'd like to spend our last 10 minutes on, which is carbocation rearrangements. And this is going to be something, again, that we're going to introduce here, but we're going to take it with us for the rest of this term and all of next term as well. It's another one of those things that's going to apply whenever you've got a reaction with a carbocation intermediate, which we won't always, but we will run into those a lot. We already know of another reaction that is a radical intermediate. What about the halogenation of alkanes? So that's a different reaction. But this reaction we're looking at here has a carbocation intermediate. And a lot of the reactions we'll learn in chapter 8 also will. Not all, but a lot of them will. So what's an example of where we'd see a carbocation rearrangement? Well, here's one that will happen to give us a carbocation rearrangement. If we treated this compound with HCl, I'm going to make it HBr just so you guys don't memorize it's a Cl. Going by Markovnikov's rule, you would predict that of those two carbons, this one here is more substituted than this one. So based just on Markovnikov's rule, you would predict this as the major product. And indeed, I think you would get some of that. But I don't think this is going to be the major product. I think the major product would look like this, because it's going to go through a carbocation rearrangement. So how does that happen? Well, it starts out looking entirely normal and as expected. This bond is going to swing out this way to pick up the proton. And again, just a side note, I want you all to be equally comfortable with drawing it like this. I don't want you memorizing the H goes on the right or something like that. This needs to be exactly the same in terms of difficulty, or of course, you probably would like to see that a little more neat than that. That's understandable. Good. I would like you guys to see those things as absolutely equal. Neither of them is better than the other. You're not going to master this by trying to memorize what goes where. But be that as it may, this is certainly a valid way of writing that mechanism. And I would expect that would give us this secondary carbocation. The hydrogen from the HBr is going to go over there. We'll now have a methyl group. Two of the H's in the methyl group were there to begin with. The other we just added in. So we'll get this secondary carbocation. And what you'll need to know about carbocation rearrangements is to look on carbons that are adjacent to the carbon with the plus charge, right next to the carbon with the plus charge, always and only those. And you will ask and answer the question, is there anything I can move over to the carbon with the plus charge to leave a more substituted or more stable carbocation behind? And I think there is. Oh, we're over here. If we move that hydride over, this is called a 1-2 hydride shift. Let me draw that real big so you can see exactly how I drew that arrow, since I know that's an issue of concern. That's how you'll draw the arrow, something like that. There's more information on that in the addendum at the end of chapter 6, class notes. So this is called a 1-2 hydride shift. The 1 and the 2 are just relative numbers, meaning that the two carbons involved are next to each other. There's a comment about the practice exam. Again, you may or may not need to worry about stereochemistry. It depends how the question's phrased. Same thing with our questions. And you need to know what hydride means. Hydride means H minus. It means a hydrogen with the electron pair. And you need to know that. You need to know that hydride and proton H plus are two entirely different critters. So hydride is not the same thing as a proton. It's a hydrogen with the electron pair and a minus charge. And that's what this arrow is showing. It's showing that the bond here, the electrons in that bond shift over to an adjacent carbon. Could be to the left or to the right. You just want to look at adjacent carbons and see if you can move something that will give you a more stable carbocation. And if we move that hydrogen over with the electron pair in the bond, indeed we will get a more stable carbocation. It will now be tertiary. instead of secondary. You'll get this carbocation. This one is secondary. If you compare to the definition we gave, then you'll have a secondary carbocation. This one is tertiary, and that's where the product comes from. The bromide ion now will attack that tertiary carbocation, and that will be, I'm quite confident, the major product. So what you need to know about carbocation rearrangements is what I said. Whenever you have a reaction that goes through a carbocation intermediate, which this one does, we know that because we've gone over the mechanism, then you need to look at carbons adjacent to the carbocation and see if there's any way to move something over in order to make a more substituted carbocation. It's not something you'll have memorized with rules beforehand. There's no way to do it by memorizing rules. You need to look at what you're given, even if it's a structure you've never seen before, and ask that question. Is there any way to move something over from an adjacent carbon so as to give me a more stable, a more substituted carbocation? In this case, the answer is yes. We can go from secondary to tertiary. That's going up in the stability stakes. I think you'll see, though, that if you moved a hydride over from this carbon, that will not help. That will give you a primary carbocation. You'll leave behind CH2+. So that's how you know it's not going to come from that carbon. It needs to come from this carbon. And again, this is just an example. I would say 1,2 hydride shifts are the most common type of situation. But other groups besides hydrogen can also migrate. And I'll end with this last example that, as I said at the beginning of class, the pressure's on in order for me to get it right. Yes? Can what, sorry? Can you do multiple carbocation shifts? It's not unheard of. They would go one by one, of course. They wouldn't go all at the same time. I think it's pretty rare in comparison to just one, though you will find some biochemical processes that do that. It's pretty fascinating. Okay, so the pressure's on. I need to do this correctly. No pressure. Okay, so to give you another example, again, I wish I had time for 10 examples, but here's another one. If we started with this alkene and we added, let's say, HCl, I'm pretty confident, let me do this right, that the major product in this case would look like that. So you're going to get a skeletal rearrangement, and it looks like a methyl group moved over. And in fact, that's exactly what happened. Let's work this out. Let's shift this bond out and pick up our proton from HCl. And again, the way you'll know what you need to put is based on how the question's phrased. But that would leave behind a plus charge on that carbon. That's a secondary carbocation. Over here, you've got a CH3. But now, we don't have any hydrogens on the adjacent carbon to move. We do have hydrogens over here in the methyl group, but that's not going to help us. If we move one of those, we'll go from secondary to primary. That's a step backwards in stability. So what we need to do is move any of these methyl groups. In this case, all three of those methyl groups are the same. So I'm going to move this one over. So again, this arrow means that the electrons in the bond, in the carbon-carbon bond, are moving over to the adjacent carbon. It will always be adjacent, always. That's why it's called a 1-2 shift. And so the electrons are going to move over to get rid of the plus charge, and they're going to bring that methyl group with them. And so, as a result, we'll get a carbocation that looks like this. And this now is a tertiary carbocation, whereas this one was secondary. Again, review your definitions. At that point, my chloride will attack, and that will give this compound. Again, it doesn't matter where you put the chlorine. You could have drawn it down here. It's the same thing. So that's how you can get a more substituted product in that way. So when you're practicing carbocation rearrangements, that's how you do it. You're always looking at the adjacent carbon to see if you can get a more stable carbocation. And the thing that I'll leave you with is, this is not just for this exam. We're going to carry this on with us for the rest of this term and also all of next term. And it will not be rare for us to run into a situation where there's a reaction with a carbocation intermediate somewhere. And in such cases, what is this one called? This isn't called anything really. It's another 1,2 shift. I guess this would be a 1,2 methyl shift. But this is nothing different from before. It's just a different kind of group shifted. So like I said, or like I was saying, we're going to run into other cases of reactions that have a carbocation intermediate. And it's at those times that I want a red flag to go up in your heads. Uh-oh, there's a carbocation here. Look out. We have the possibility for carbocation rearrangements. And so if there's a way for your intermediate to rearrange to give a more stable one, that will happen. So this doesn't just apply to this exam. This is going to be relevant going forward. And I am out of time. Can you only shift methyls and hydrogens? No, and you will get an idea of what other things you might be given from the OWL problems. Could you have moved the chlorine to any of the 3 bonds connected to the closest carbocation? You could have put the Cl here, you could have put it here, or you could have put it there. I see those as the same thing. So you guys need to practice until you also see those as being the same thing. But I'm out of time, so have a great day. I will see you all on Friday.